Welcome back to Maths with Mrs. J. I wanted to do something kind of interesting today and show you how you would go from an unknown function, y equals f of x, I haven't given the formula for it, how you would go from the graph of that to getting a sketch of what the derivative would look like and what the second derivative would look like. Now, you can probably already notice that I have marked some crucial points on our original function. In dark green, I've marked local maximum, local minimum, horizontal point of inflection, and a local maximum. We should know by now that at any stationary point, the first derivative will be 0. So let's actually go in and pop that onto our axis there, that we already know that at these points here, I'm going to do it slightly bigger. At these points here, we're going to have a 0 derivative. I have marked in yellow lines, the points of inflection. Now, of course, a horizontal point of inflection is a stationary point and a point of inflection. Not only is the tangent to the curve horizontal there, but you also have a change in concavity of the graph. So here, our second derivative will also be 0. Our second derivative will also be 0 for these points here, where you had your oblique points of inflection. So we're going from concave down to concave up, then from concave up to concave down, then concave up again, and then concave down again. So whenever you have a change in concavity, you are going to get your second derivative 0 as well. Nothing particularly interesting as far as the concavity happens after this point here. It's concave down for the rest of the graph. All right, now let's have a bit of a look, and I'm just going to put some notes in light pen, shall we say, or call it pen, just to talk about what's happening to the derivative here. For this section of the graph, we know that the derivative is positive, it's going up, but it is decreasing. So it's becoming less steep until it comes to this 0 here. So we could have something like this. So it's coming down and decreasing, right? So it's positive and decreasing. For this section here, obviously the derivative is 0 here. We're negative and decreasing. It's getting increasingly steep, isn't it? So we're negative and decreasing until we get to this point. We don't know how low to put it, but that's okay. So, and then we are negative but increasing back up to our 0. Notice that a point of inflection in your original curve becomes a turning point in your derivative, which is kind of cool. All right, now what's happening? We've got a derivative of 0. The tangent to the curve is momentarily horizontal. From here, your derivative, your curve is getting increasingly steep, isn't it? In a positive direction. So it's coming up here, something like this, until momentarily it stops increasing and then it starts decreasing again. So it's still positive, but see how it's getting steeper and then it's getting less steep? So we're going to have something like this happening here until it comes down to 0 again. In this little section here, we have a positive increasing gradient. All right, so probably what we need to do, let me just undo this bit here, because what we're going to actually need to do, I think, is something like this. All right, so it's positive and increasing, and then it's positive and decreasing and then it's negative from there on. So we're going to get something like that for your y equals f dash x graph. So the crucial things to know are that wherever we have a stationary point in our original function, whether it be a local maximum, a local minimum, or a horizontal point of inflection, we must have a 0 for our derivative. Also, wherever you have a point of inflection, whether it be oblique or horizontal, we're going to get a turning point in our gradient. There's going to be an extra bit of excitement, shall we say, here. We've got turning points here, here, and here. But because of this business here, we're also going to have some extra changes in concavity. So let's just bear that in mind. They will be important points when we come down here. Let's actually pop in some vertical lines just coming down through here. We'll just move that across and through here. Again, we'll just move that across. Okay. So that's a rough idea of what our first derivative would look like. Okay. We've already marked in from our original function, we know that our second derivative will be 0, where I've marked here. Wherever you had a point of inflection, changing concavity, it will be 0. Let's also now have a look at this function and see what it's doing. So here, the function is decreasing, all right? It's going down, the gradient is negative, but becoming less negative, okay, until the point where it becomes 0 here. So it's something like going up like this. Then it's going to be positive and continuing to be positive until you get to this point, when it will start to decrease though. It'll still be positive, but it will be decreasing. So let's have a look how we would do that. We would do something like maybe, something like that. Right? So we're positive, but we're decreasing. At this point here, this is an oblique point of inflection in our first derivative. This little bit here, we've got concave down, it's negative gradient, and it's getting increasingly negative, and then it's becoming decreasingly negative until it's 0. So we're going to get like a local minimum happening there. You just fix that up, that wasn't the best. Local minimum happening in here somewhere. And in this little bit here, the gradient of this is positive and increasing, and then positive and decreasing. So we've got this sort of scenario where we've got a local maximum. Then the gradient of this from then on is just going to be negative. Negative and potentially decreasing. So, you know, something like that. So there you have it. It's kind of interesting to see how, even without knowing the function itself, by knowing information about stationary points and points of inflection and what that signifies in terms of the gradient, we can get a rough sketch, and this is a very rough sketch. I'm not in any way, shape or form pretending that this is perfect. We get a rough sketch of what the first derivative is going to look like and the second derivative. Let's just go over some key points here again. Wherever your stationary points are in your function, your first derivative will be 0. Wherever your points of inflection are in your original function, whatever sort of point of inflection they are, your second derivative will be 0. Where you have a oblique point of inflection, or any point of inflection in your original function, will be a turning point in your derivative, and that of course becomes your 0 second derivative there. And whenever you have a point of inflection in your first derivative, you have a turning point in your second derivative. I think that's kind of cool. Don't know if you agree with me or not, but it's kind of cool. You can actually go backwards, which is even harder. I'm not going to attempt that at this stage, but I will at some stage in the future do a video where you go backwards from the second derivative and you try to work out the shape of the first derivative in the original function.